This is Elaine McCormick reporting for Physics 2 on Public Lecture 1, Supermassive Black Holes. In this lecture, we learned about supermassive black holes, which are measured as solar mass units versus dispersion of nearby stars. One solar mass unit is equal to 1.989 e to the 30 kilograms, and supermassive black holes are generally much larger, ranging above 10e5 solar mass units. They are also defined by their angular momentum, which is measured by a dimensionless spin parameter alpha. Alpha equals Cj over gm squared, and ranges between the values of 0 and 1. 0 represents no spin and corresponds to a Schwarzschild black hole, whereas 1 represents maximum spin, corresponding to a Kerr black hole. Furthermore, we looked at the galactic center, which is the rotational center of the Milky Way and lies in the constellation of Sagittarius. It is blocked from sight by a dust screen, but is penetrable by radio and infrared wavelengths, which we can use to get a visual on this area. Sagittarius A star represents the non-thermal intense radio source at the center of the galactic center, which is pretty much immediately in the center of the Milky Way, which is our galaxy. Adaptive optics have been used to detect young stars moving around Sagittarius A star, which coincides with the fact that there is a supermassive black hole there at the very center of the Milky Way. So, branching off of this, supermassive black holes are found in many other galaxies, and they're often at the center of almost all massive galaxies. Scientists, or astrophysicists specifically, look at active galactic nuclei, which are systems that accrete material and shine brightly. They're compact centers found at the center of galaxies and can be measured by their energy, which converts gravitational energy into thermal energy. All accreting black holes produce X-ray emissions, which makes them shine brightly, and comes from the inner regions due to rapid variations. The inner edge is representative of the accreting disk, and when we mentioned earlier different types of black holes, the radius of these disks and representative of the types of black holes can be seen here, where Schwarzschild black holes have a radius of about 6 times gm over c squared, whereas Kerr black holes have a radius just of gm over c squared. Next, we looked at how black holes coincide with galaxy evolution. Black holes and their host galaxy have a common evolution. Black holes grow by accretion and shine as active galactic nuclei, so we can view them as astrophysicists using appropriate materials. The mass of black holes has been found to directly correlate with the size of the galaxy and the orbital speed of outer stars circling around in the galaxy. The final points on this lecture were that supermassive black holes are an essential part of modern astrophysics. Black hole environments are extreme, and the galactic center corresponds to an up-close study of black holes. Active galactic nuclei display the interaction between properties demonstrated by black holes and their host galaxies. Finally, I wanted to look a little bit more into black holes because getting a good understanding on these is hard because they're so massive. So if you look at this visual, you can see the tiny dot in the middle is Earth's orbit, and then Neptune's orbit is just the blue ring outside it. But if you want to look at the size of a black hole, which corresponds to 4 light days, it's extremely large compared to Earth's orbit, circling the whole sun in only 17 light minutes. Also, this is kind of a hard visual to see, but size ranging up in the galaxy and the universe. We have Earth, which is just a dot in the solar system, which is just a dot in the solar interstellar neighborhood, which is just another dot in the Milky Way, and furthermore, in the local galactic group, the Virgo supercluster, the local superclusters, and finally, the observable universe. So that's the size of our universe, and it's crazy. Just to look into some of the astrophysics behind it,